Good morning, students. Welcome to Machine Integration live lectures. In this class, we'll discuss about functions of bounded variation. Okay. So you take f. Just we'll recall some notation which we have used already. We have what is meant by f plus. It is positive. Given any function f, how f plus is defined? It is positive part of f. Okay. And so this is positive part of f. Obviously, how it is defined? Maximum of f of x comma 0, and f minus is negative part of f, which is maximum of minus f comma 0, right? And what we have seen, that any f can be written as f plus minus f minus, and absolute value of f is f plus plus f minus, right? We have seen these things or not? For any function we have this, right? Then now we'll define few things. So let f be a real valued function defined on a comma b. Okay. Now let x say suppose a, which is equal to x naught less than x1 less than x2 xn, which is equal to b, right? Or you write k, suppose xk be a partition of this interval a comma b. So take a partition of a comma b, you denote that x naught x1 up to xk. Then we can have this small p. Okay, this is positive part of summation, this f of xi minus f of xi minus 1. You take this and you take the positive part of this function from I is equal to 1 to k. Is this clear? What is this small p? How we have defined this small p is f of xi minus f of xi minus 1. Then take the positive part of that function. Whatever new function you are getting, for that you take the positive part, right? Similarly, small n you can define as, so you just set these values. Okay, this is negative part of this f of xi minus f of xi minus 1 minus. Okay, and t, the small t, which is absolute value, I is equal to 1 to k f of xi minus f of xi minus 1, right? Is this three notations clear? Actually what we are finding, we are
Yes, sir.
finding the something like some difference, f of xi minus f of xi minus 1, then take the positive part of that function, right, over this summation. Now you can observe that the relation between this p, n and t, what you can observe is that then this mod f of xi minus f of xi minus 1 is same as, because it is just like mod f, right? Mod f is same as f plus plus f minus, right? So therefore t you can write as, because this is mod f minus fi minus 1, which is same as p plus n. Is that clear? Huh? Yes or no? Because this you
Yes,
can
sir.
write as I is equal to 1 to k instead of mod f. Mod of f means mod f of xi minus f of xi minus 1. This we can write as f of xi minus f of xi minus 1, positive part of this function, minus, okay, f of xi minus f of xi minus 1, negative part of this. Okay, then you take the summation inside, what you will get is, the first one is p and the next one is n. So you get that p is equal to p minus n for any given partition. Okay, now you change the partition and you find these values. Okay, right? Then we can talk about supremum of those values, whatever we are getting. So we'll set three values, this capital P, which is supremum of this small p, supremum of small p, and uh, capital N is supremum of this all n values n, and capital T is equal to supremum of this T, where supremum is taken over all possible partitions, all possible partition of partitions of A comma B, right? So you will get these three values. Okay, then you can observe that because this so here you can also write this T, right? And what is the relation between P and what can you say about P plus N? Huh? Just a second. We did somewhere wrong, right? Where nobody is noticing. Are you seeing or not? Because this mod f is equal to f plus plus f minus, so it is not plus here, right? It is plus here. Huh? Have you
Yes,
noticed?
sir.
This is plus.
Yes, sir.
And then you have to inform, right? Hmm? So this is t is equal to p plus n, not minus here. If I don't even notice, then you will simply accept it. Huh? So this t is equal to actually p plus n, not p minus n, because this is the how value is defined. Absolute value of f is f plus plus f minus. Okay, right? So this is p plus n. That means in particular, you can see that p is less than or equal to t because they are all positive values, right? And also n is also less than or equal to t, right? Now this capital P and capital T we also denote sometimes by this PAB, okay, and NAB TAB, because just to mention this A comma B, which interval we are taking and what are the partition of A comma B we are taking, right? And now we will define with this notation, we'll define that a real valued function defined on this A comma B, real valued function f, you call it here f, okay, defined on A comma B is said to be of bounded variation if this t is finite. Okay, whatever value we are getting this t supremum, that should be a finite value. Okay, if t is finite. Okay, so sometimes this whatever these values we are having, we can as I already said here, this we also denote by, so also we denote by PAB, okay, similarly NAB TAB, okay, even or also TABF PABF or NABF. Just to use that, F is defined on A comma B. So these are all different notations. Just to whenever you have some two different intervals, then when you talk about that P, then you denote this by PAB. So this PAB denotes what? This is the supremum of these values, and over partition you take different partitions of A comma B and you find the supremum, right? Or you can write like this, or that is same as the TAB is finite or TABF, all are same notations. Okay, so whenever this value whatever we are having, that is if it is finite, then we say that it is of bounded variation. So if necessary you can call it this as T, which is total variation, P is positive variation, and N is negative variation of F. Okay, so this P denotes positive variation, N denotes negative variation, and T you can call it as total variation. So we say that it is a bounded variation if total variation is finite. Okay, is that clear? Hmm? So
Yes.
we call this PAB, okay, A of F as positive variation of f and this NAB of f as negative variation of f, and this TAB of f we'll call it as total variation of f, right? So with this notation, if a total variation is finite, then we say that f is of bounded variation, right? So therefore f is of bounded variation if this total variation of f is finite, right? If total variation of f is finite. So basically what you have to understand is, if you want to find bounded variation of given function, whether it is a bounded variation or not, then we have to calculate the total variation and see whether it is finite or not. Is that clear? And given interval, yes or no? Hmm? Because the definition is
Yes,
defined
sir.
for over total variation. So we have to just check whether total variation is finite or not. If total variation of that given function is finite and this given interval a comma b, then we say it is a bounded variation, or otherwise it is not bounded variation. Is that clear? And now total variation, how it is calculated? This is total variation, right? This is called total variation supremum. You have to take supremum of all such values. So take any partition and find this value, and take another partition, find this value and find supremum. Is that clear? So let's see some examples to understand better. Okay, so take some example. So first take uh, f, suppose a mono increasing function. Okay, so if f is increasing and interval a comma b, then f is of bounded variation. F is of bounded variation, and in this case, the total variation TAB, okay, is nothing but f of b minus f of e. The function evaluated at this point end points f of b minus f of e. Okay, let's see why this is true. So from this we will get n number of examples. Just take any increasing sequence, a increasing function, sorry, you take any increasing function and a comma b, then you will see that it is of bounded variation. And what is the value of total variation? Is simply function evaluated at those endpoints f of b minus f of b. Is this clear? Hmm? Is statement clear? We have not yet proved, but we'll prove it. It is not at all difficult one. Yes or no?
Yes, sir.
Yes, sir.
No. So as I said, if you want to calculate a total variation, what we have to do? You take a partition and find the value, that small t, and then you take the supremum. So to find that, start with a partition. Let say suppose this a, which is equal to x naught, okay, right, less than x1 up to x k or xn, whatever you take, which is equal to b, okay, be a partition of this interval a comma b, right? Then what is this t value? If you want, you write t a b also, there is no problem. This, like this also you can write, just to mention that this is the value regarding this particular partition. Okay, what is this value? Is summation mod f of xi minus f of xi minus 1, where I is from 1 to k. Is this clear? Yes or no? Hmm?
Yes, sir.
Now what can you say about, because f is an increasing
Yes.
function, f is increasing, as f is increasing, and this xi minus 1 is strictly less than xi, because of that is a partition, right? So what we get, what can you say about f of xi minus 1 and f of xi is this one. Is this clear? Yes or no?
Yes, sir.
If you want, you can write equal also. It is not a problem. So f of xi minus 1 is less than or equal to f of xi. So therefore, this absolute value, huh, this implies this f of xi minus f of xi minus 1 is greater than or equal to 0. Is this clear? Right? So now because it is greater than or equal to 0, this absolute value is same as the difference. Yes or no? Hmm? Therefore, our TAB is nothing but summation I is equal to 1 to k. Instead of this absolute, what we have here is simply f of xi minus f of xi minus 1. Yes or no? Hmm? Because those
Yes, sir.
values are all non-negative values. So absolute value is same as itself, right? But if you expand this one, what you will get? Huh? It is simply when you put x is equal to I is equal to 1. This is f of x1 minus f of x naught, right? First term. Then next time f of, when I is equal to 2, it is f of x2 minus f of x1, right? Plus and so on. What is last one? When k, it is f of xk minus f of xk minus 1. Is this clear? Right? Now you see that many terms will get cancelled. This f of x1 will get then this will get sorry, what we have here is this will get cancelled with this one, right? Now f of x2 will be get cancelled with next one and so on, right? So what is, everything will be there, this will be get cancelled with the previous one, right? So what are the terms only remaining? Only terms remaining is this f of xk,
If
okay, because that won't be get cancelled. So f of xk is remaining and this term is get remaining, f of x naught. But f of xk is our b and f of x naught is our e. So we get that this value, however partition it may be, we are getting that value as f of b minus f of a. This implies our tab, which is equal to supremum of these values, right? But here it is not depending on that partition. That is same as f of b minus f of. Are you following? Yes or no? The value what we got here is not
Yes, sir.
depending on this xi's, okay, except end point and starting point and end point. In between it is not depending. So no matter which partition you take of this a comma b, this value is always same, f of b minus f of b. So in particular, supremum among all these values is also equal to f of b minus f of b. Okay, so therefore, and of course it is a finite value, right? This is a finite value because f is a real valued function. Yes or no? Huh? So any increasing function, you can see that it is bounded variation. What can you say about decreasing function? Hmm? What can you say about if it is a decreasing function? Similarly, you can try. Where is the difference? Only in place of f of xi minus f of xi minus 1, because this value will become less than or equal to 0, right? So mod x is, if x is less than or equal to 0, mod x is minus 6, right? So here you will have f of xi minus 1 minus f of x. That means only thing is f of a minus f of b you will get. Yes or no? Hmm? So no matter whether it is increasing or decreasing, every monotone function is of bounded variation. Is that clear? Huh? Right?
Yes, sir.
So if it is decreasing, only thing is you will get f of a minus f of b. That is the only difference. Right? So just to now let's see another example. So example 2. So so suppose if your function is a ellipsis function which satisfies the ellipsis condition, you know what is meant by ellipsis function. So every every ellipsis function is of bounded variation. So we are giving again n number of examples. So if some function is it satisfies, if it satisfies ellipsis condition, then we can say that, we can prove that it is of bounded variation. Okay. So what is meant by saying ellipsis function? Huh? So let f be a ellipsis function. Of course, every time we have ellipsis function defined on this interval a comma b, because we talk about bounded variation defined on closed and bounded interval. Okay. So f, let f be ellipsis function on defined on a comma b, right? That is, what is the meaning of saying that it is ellipsis function? F of x minus f of y, whenever you take this value, is less than or equal to some alpha times mod x minus y, right? Yes or no? Hmm? So if you want there exist alpha, right, greater than 0, which is a real number, such that mod f of x minus f of y is less than or equal to alpha times mod x minus y. Huh? Whether you know this, when we say that some function is ellipsis function, yes or no? Hmm? Hello?
Yes.
So whenever a function satisfies this condition, then we say that it is ellipsis. Huh? In basic real analysis course, you have this definition, right? Now we want to show that it is of bounded variation. So to show that something is a bounded variation, we want to show that total variation is finite. For that, start with a partition. Okay. So let again x naught, which is equal to a, x1, xk, b. Okay. A partition. You take some general partition of a comma b. Then we will find what is the t value and see what we will get. Right. Then this t is nothing but, what is t value? Is summation mod f of xi minus f of xi minus 1, I is from 1 to k, right? But by using this condition, this f of x minus f of y is less than or equal to alpha times mod x minus y, right? So we can make it, this is less than or equal to, the whatever inside you have is less than or equal to alpha times, so alpha times mod xi minus 1 we get. Is this clear? Yes or no? Hmm? Because your f mod fx minus fy is less than or equal to alpha times mod x minus y, but your xi minus 1 is strictly less than xi, so this absolute value is actually same as, so this value is same as alpha times summation I is equal to 1 to k. This is simply xi minus 1. Okay, right? But again, by if you expand this series, finite series, all terms except first term and last term will get remaining all will get cancelled. So what is this one? Is alpha times the x naught will remain and xk will remain. Okay, this is xk, sorry, and here it is x naught. Just like how we have seen in the previous example, only those two will remain, remaining all will get cancelled. That is same as b minus e, right? So what we have shown is that no matter what partition you take, this is less than or equal to alpha times b minus a for every partition, right? For every partition of a comma b. This implies when you take supremum, that is capital T a comma b, which is less than or equal to supremum of t, right? That is also less than or equal to alpha times b minus a, but we know it is finite, right? This shows that this f is of bounded variation. Okay, we know, you might have seen, if a function is differentiable, that means f dash of x exists, then if you see this one, if f dash of x exists, then you can see that it satisfies ellipsis function. Okay, right? So therefore, if a given function is differentiable, then we can say that it is of bounded variation. The converse not necessarily true, but if it is continuous, we cannot. Are you following what I am saying? By using this, we know that every differentiable function is ellipsis, so every differentiable function is of bounded variation. But it is not true if that is just continuous. Or in other words, we give an example of not bounded variation. Okay, so let f of define f of x as x into cos pi by 2x if x is strictly between 0 and less than or equal to 1, and 0 if x is equal to 0. Okay, that means we have defined f on the closed interval 0 comma 1 as this. Okay, then we will show that this f is not of bounded variation. Okay, but one can observe that f is continuous here. Okay, so you can write this statement, then f is not of bounded variation. That means, see, when we want to show that something is not of bounded variation, what we want to show? We want to show that this capital T, A, B, it is not finite. Okay. So it is enough if we show that for some particular type of partitions, that value is not finite. If it is infinite, then supremum is also infinite. Right? Okay. Are you with me? Hmm? If at all we want to show that
Yes,
it is
sir.
not of bounded
Yes.
variation, you try to take some particular type of partition and find the that variation and see whether it is show that it is not finite value. Okay, then we are done that it is not of bounded variation. So whenever you want to show that something is not of bounded variation, then for a particular type of partition, show that that small t whatever we are talking about, okay, it is not a finite value. When taking that suitable partition, that is not a finite value actually. Okay, fine. So for this, first observe that limit f of x as extending to 0, that is limit extending to 0 x cos pi by 2x. This value you can check that what is the value of this? Huh? This is same as saying that limit extending to 0 cos pi by 2x upon, you can bring it here as 1 by x, then you multiply by pi by 2 here, right? Then you just divide by pi by 2. Okay, but this is same as just like limit extending to 0 cos x upon x, which is 0. So therefore this entire value is 0. This is same as f of 0, right? So this implies f is continuous at 0, and remaining all places it is continuous because it is a product of two continuous functions, right? And hence f is continuous on this closed interval 0 comma 1, because there is no problem. It is only problem is that if x is equal to 0, at x is equal to 0 anyhow it is continuous. Is this clear? So this is a continuous function, and we will show that now it is not bounded variation. Okay, so not every continuous function is of bounded variation, right? But by this previous example, every differentiable function is of bounded variation. Okay, because even we require a weaker condition. If it satisfies a Lipschitz function, then it is of bounded variation. Fine. Now, how we'll show that it is not of bounded variation? We'll consider, so consider a partition for any natural number, call it Pn, which is we want to partition this 0 comma 1 in this way. 1, or you call it 1 by, so you can write 1 by 2n, okay, 1 by 2n minus 1, 1 by 2n minus 2, and so on. Then last it is you can call it say 1 by 3, 1 by 2, okay, then 1, and you can put it 0 anywhere you want. Okay, so if I want, I will put it here in beginning itself. So 0, then 1 by 2n, 1 by 2n minus 1, 1 by 2n minus 2, and so on. Okay, just like for example, so if you want, for example, if I take n is equal to 1, then what is this p1? 0, and when n is 1 here, it is 1 by 2, then 1. Is this clear? And what is p2? For n is equal to 2, for n is equal to 2, what is p2? Tell me someone. When n is equal to 2, what you will get here? What is this partition? Huh? 0,
0,
0.
1 by 4,
1 by 4, then 1 by 3, 1 by 2 and
Yes.
1. Is this clear?
1.
Okay. Okay, and so on. We are taking some particular suitable thing so that when you apply here, depending on this function we are taking, that nothing else. Because when you substitute those points, you get just like cos n pi r cos n pi by 2, just like that. Okay, because here 2 times x is there, so because of that we are taking multiples of 2 and then add and so on. Now, for this partition, we will try to calculate what is that t value and see what we will get, right? Then, what is t? This t, for this t, it is summation mod f of xi minus f of xi minus 1 I is equal to 1 to k, right? For this partition, if you simplify this, what you will get is that, so this is your partition x naught, this is your x naught, x1, x2 up to xk, which is last one, right? So if you substitute those values here, the first one is f of x1 minus f of x naught plus next one is f of x2 minus f of x1 plus next one is f of x3 minus f of x2 plus and so on. What you will get, the last one is mod f of xk minus f of xk minus 1, right? And now if you substitute f of x1, what is f of x1? Our x1 is this 1 by 2n, right? So let me put those values if necessary. F of 1 by 2n minus f of 0, because x naught is 0, right? Plus, what is our f of x2? Our x2 is 1 by 2n minus 1. So f of 1 by 2n minus 1 minus f of 1 by 2n plus, and what is f x3? This is x3, which is 1 by 2n minus 2 minus f of 1 by 2n minus 1 plus and so on. The last term I will don't write, you will get from this itself. Okay. Now if you substitute these values, what is our f of x when x is not equal to 0? It is x times cos pi by 2x. Okay. So x times, so this is our x. At present, this is our x, right? This much is our x. So this is nothing but 1 by x, which is 1 by 2n cos pi by 2 times x. Okay, so this x will be, x is in denominator and our x is just like 1 by 2n. Are you following? Yes or no? So it is just like 1 by x.
Yes.
So what you get here is like this. Is this clear? And f of 0 is 0. Okay, plus next one, f of 1 by 2n minus 1. So this x is 1 by 2n minus 1 and cos pi by 2 will be always there, and the next one is 2n minus 1 because it is 1 by x. Are you following? Minus, and f of 1 by 2n we have already written there, cos pi by 2 into 2n, right? Plus we'll just write one more term so that you will understand. What is next term? It is f of 1 by 2n minus 2, right? Which is 1 by 2n minus 2, 1 by 2n minus 2 into cos pi by 2 into 2n minus 2 minus, what is f of 1 by 2n minus 1, which we have already calculated here, 2n minus 1 cos pi by 2 into 2n minus 1. Okay, plus and so on. That last term, whatever it is there, you keep it. It is not a problem. Now, if you see the first one, this 2 will get cancelled, right? And what you have is cos n pi. We know cos n pi, no matter whether n is even or odd, cos n pi is minus 1 whole power n, right? Yes or no? Huh? What is cos n value? Cos n pi value is either plus 1 or minus 1 depending on n is even or odd, right? But you are taking absolute value, so therefore absolute value of minus 1 whole power n is anyhow 1 only. So what you get here is, first time you get 2n. Is this clear? This value, whatever we are having, that value is 1 by 2n. Yes or no? Next one, what can you say about
Yes.
this? Huh? Because no matter whether n is even or odd, this value 2n minus 1 is odd. This one is odd or not? Huh? 2n minus 1 is an odd number. So if n, whatever you are having here, if it is odd, then cos, just like say m pi by 2, if m is odd, that value is always 0, right? So this value is, whatever we are having, this value is 0. Okay, and this is nothing but again 1 by 2n. Yes or no? Any problem? Huh? So what things we
No,
are
sir.
using?
No, sir.
Since one is cos n pi is always minus 1 whole power n, and cos m pi by 2 is 0 if m is odd, right? So here this 2n minus 1 is odd, so cos m pi by 2, that value is always 0. Now similarly come here, what is this value now? 1 by 2n minus 2. Now in this I can take 2 common, right? 2n minus 2. So if I take 2 common, it is n minus 1. 2 will get cancelled. So it is just like cos, what is this one? This is nothing but cos n minus 1 into pi. Yes or no? Whatever you are having here, this is same as cos n minus 1 into pi. But that value is again, by using this one, it is minus 1 whole power n minus 1, then you are taking absolute value, that value is anyhow, when it comes to here, this value is
But
0, because we already seen that one, right? So what we have here is 1 by 2n minus 2, and absolute value of minus 1 whole power n is 1. Is this clear? Have you understood why this is 1 minus 2n minus 2? 1 upon 2n minus 2? Huh? Any problem? Because this value, whatever you are having, one is 0, the other one is minus 1 whole power n. N in the sense, you can say minus 1, if you just write here, instead of using m, you write m, so that you will have easy understanding. Yes or no? Hmm?
Yes, sir.
yes,
Okay. So it is, if cos m pi, it is minus 1 whole power m, cos m pi by 2, where m is odd, okay, then it is 0, right? So in this, every term you can observe that one time definitely it will come odd, so that value anyhow goes to 0. The other one is minus 1 whole power n you will have, okay, so you will get only such like this. So but next time again, because this term whatever you are talking about, it will come here in the next term, so again one more time this will come, plus and so on. Yes or no? So you can see that every time one value repeats again and again. Okay, right?
Yes. Yes.
Okay.
yes,
So
sir.
so what is this? What is last term? Can you see what is last term? Hmm? What is for last value? This n. Then we are getting. See, if you write this one, it is same as 1 by 2n, right? Then it is 2 into n minus 1. It is also 2 into n minus 1 and so on, right? Yes or no? So if you see here, what you will get is 1 by 2 plus 1 by 2. Is that clear? Hmm?
Sir, repeat.
So this 1 by 2n plus 1 by 2n, next 1 by 2n minus 1 plus 1 by 2n minus 1. Next time it is 1 by 2n minus 4, 1 by 2n minus 4, like that you will get, right? So two terms you will get same. So what is last term you will get is, because here I can take this as 2 times n minus 1. This is 1 by 2n. Next time what we got is 2 into n minus 1. Next time what we are going to get is 2 into n minus 2 and so on. So what you will get is, everything is a multiple of 2. So at the end what you will get is 2 times 1 plus 2 times 1. Are you following? Hmm?
Yes, yes, sir.
So if you see this and add, what you will get, because this is 1 by 2n plus 1 by 2n, so which is same as 1 by n, it is again 1 by 2 into n minus 1 plus 1 by 2 into n minus 1, so you will get n minus 1 plus 1 by n minus 2 plus and so on. If you see this one, this is same as 1. Are you following? Yes or no? Hmm? So therefore, this is
Sir.
same as
Yes.
summation 1 by k is equal to 1 to n. Is this clear? So for every positive integer n, what we got this value is that summation k is equal to 1 upon k is equal to 1 to n, right? So therefore, if I take n as large as possible, what we know about this? This is a geometric series or not? Huh? This value as n tending to infinity, what we know? This value diverges, right? It is a geometric series. Yes or no? Hmm? So
Yes, sir.
as n tending to infinity, this summation 1 by k is equal to 1 to n, this tends to infinity. Is this clear? So therefore, this value, whatever variation we are getting that value as infinity. Therefore, this TAB, right, is also infinite, which is equal to supremum of such values, right? But when one of the partition what we are taking is take this limit n tending to infinity Pn, that is one partition. Okay, that value what we got is infinity. So therefore, this is also infinite. Is this clear? This implies f is not of bounded variation. Any problem? No? Have you understood what we did? You have to take a suitable partition and apply calculate these values and see whether you get a geometric series or not. Geometric series. Then we know that geometric series diverges. Okay. So therefore, that is not a finite value. That means total variation is not a finite value. Hence, it is not a bounded variation. Okay. Is that clear? No? Now take
Yes.
exercise and check whether you will get this problem or not. I'll give that exercise. Where is that? Fine. So this one, f of x is equal to x square cos 1 by x square if x is not equal to 0 and x belongs to minus 1 to 1. Okay, and 0 if x is equal to 0. Check whether is f bounded variation, f is of bounded variation or not on this interval minus 1 comma 1. And second one, say g of x similar, but only thing is it is cos 1 by x. Okay, x is not equal to 0 and x belongs to minus 1 to 1 and 0 if x is equal to 0, right? Is check is g of bounded variation or not on this interval minus 1 to 1. See, one thing you can observe, first out of this f and g. Okay, if you see this, try to find differentiation, whether differentiation exists or not. If differentiation exists, then it satisfies Lipschitz condition, then it is clearly is of bounded variation,
Bound.
right? So among these two, you see anyone whether it satisfies Lipschitz condition or derivative, whether derivative exists or not. Okay. If you have any difficulty, you ask next class. Now we go to some of the results with this several examples. We'll see some properties of bounded variation. Okay. The first lemma is that if f is of bounded variation, say on this interval a comma b, then this you can this TAB, the total variation is nothing but PAB plus NAB. That means the total variation is nothing but sum of the positive and negative variations. Okay, and not only that, this f of b minus f of a, this value is equal to the difference of PAB minus NAB. Okay, is statement clear? What lemma says is that
Yes.
if f given function is of bounded variation, then the total variation is sum of those two, and difference of these two is nothing but f of b minus f of b. Okay, It is not at all difficult. Proof is that, let's see where we have defined this TAB and here. Okay, this TAB, right? And T small t is equal to P plus N, and so because T is equal to P plus N, and what can you say about, we want to find this f
Yes, sir.
of B minus f of A, f of B minus f of, in terms of f of B minus f of A we want to find, right? So here this, if you calculate what is P minus N, here we have not calculated in this. If you check P minus N, because we know f is equal to f plus minus f minus, so if you take P and then N, P minus N, what you will get is same as, so you can solve here, because P is equal to summation f of xi minus f of xi minus 1, positive part of this, okay, and what is our n is summation, so here I is from 1 to k, and I is equal to 1 to k, this f of xi minus f of xi minus 1 minus, okay, where this x naught up to xk is partition of this a comma b, okay. Then what can you say about this P minus N? You can check that this is equal to I is equal to 1 to K f of xi minus f of xi minus 1 plus, and then minus of this f of xi minus f of xi minus 1 minus, right? So therefore this is just like f plus minus or g plus minus g minus, which is same as g. So therefore what you have here is I is equal to 1 to K f of xi minus f of xi minus 1, right? Now again you expand this and all the terms will get cancelled except 2. What is that? Is nothing but f of this xk minus f of x naught, but xk is b, so you get f of b minus f of a. So therefore p minus n is equal to f of b minus f of a. This implies p, suppose if p is equal to n plus f of b minus f of a, right? This p is equal to n plus f of b minus f of a. Therefore, what can you say about this t? This implies our t, which is equal to p plus n. So this is same as n plus this one. So 2n plus f of b minus f of a we will get, right? This implies if you take supremum of t, right? Supremum of t, which is nothing but 2 times supremum of n plus f of b minus f of a. Is this clear? Huh? If t is this, then you take supremum of all such partitions, you get supremum of t is equal to 2 plus supremum of n of this, right? But supremum of t is nothing but tab, and this is nothing but 2 times n, or you write nab plus f of b minus f of a, right? But this is same as, again I can write this as nab plus nab minus f of b minus f of a. That is same as, huh? That is same as pab or not? This is same as nab plus f of b minus f of a, right? But this is same as pab. Why? Because our p is nothing but from this. Is this clear? Because our p is equal to n plus f of b minus f of a. So if you take supremum of over all partitions, capital P is equal to capital N plus f of b minus f of a, which is this. Is this clear? So therefore what we have proved is that TAB is equal to NAB plus PAB, and also from here, if you want, you take this as star, and also from star, this PAB, which is equal to NAB, right, plus f of b minus f of a. This implies our f of b minus f of a is equal to PAB minus NAB, right? Okay, so that is what we want to prove. Now tell me where we have used the fact that f is of bounded variation. Hmm? Where we have used the fact that f is of bounded variation. Because if you see all these things, huh? because because f is of bounded variation, so your TAB is a finite value. Therefore, this TAB is PAB plus NAB, right? Or from here, this PAB and NAB. So you can check that. So observe that when you are taking this side, we have to make sure that this NAB is finite, right? So since f is of bounded variation, this implies TAB, this value is finite. So this implies PAB as well as NAB, they are finite. So you can bring it this side. Is this clear? Hmm? So if f is of bounded variation, then their sum is TAB and difference is f of b minus f of b. Okay. Now we'll prove an interesting result which is by due to Jordan. So you can also call it this as Jordan theorem, which says that any bounded variation, if f is of bounded variation, then it can be written as difference of two monotone real valued functions, and it is if and only if. So the statement is uh, let f be a real valued function defined on closed interval a comma b. Okay, then f is of bounded variation, f is of bounded variation if and only if and only if f is f is the difference of f is the difference of two monotone real valued functions, monotone real valued functions. That is, so if you write in short, f is of, say, I'll write simply BV just for bounded variation if and only if f is equal to, say, call it g minus h, where g and h are monotone functions. Is statement clear what we want to prove? Hmm? Yes or no? Hello?
Yes, sir.
What we want to prove is that if,
F is
say, suppose
bounded
f is of
and
bounded variation,
difference.
then we want to show that f can be written as difference of two monotone functions. Okay, conversely, whenever f is of difference of two monotone functions, we want to show that f is of bounded variation. Okay, so let's do this. It is not at all difficult. So first assume that, say, let f be of bounded variation. That means that TAB, whatever we are having, this is a finite value, total variation is finite. We want to show that somehow there should be two functions g and h such that f is equal to g minus h, where g and h are monotone. Okay, so we will define two functions. So g of x, of course g and h also we define on closed interval a comma b. So define g of x as the PAX. We know already this notation, right? What is meant by this one? It is supremum among all those positive values defined on the interval what? Huh? For the
A
partition
to
a
X.
comma x, we are defining g of x. Is this clear? Yes or no? And
Yes, sir.
h of x as this nax. What is this PAX denotes? Hmm? So PAX denotes, so this, for instead of taking partitions for a to b, you take partition for a to x. Okay, then take this supremum value, that is your g of x. Are you following? Similarly for na of x. So we will try to get different partitions for this a to x, and among, we will calculate those values and find the supremum, right? Okay, Now we will show that clearly f is equal to g minus f of x is equal to this pa of x minus na of x, which you can see that it is same as f of x, right? So only thing we want to show that this g and h are monotone and real valued functions, right? So we will show that our claim that this g and h, okay, so this g of x is monotone. Same way you can show that h of x is also monotone. So if we want to show that some function is monotone, what is meaning of saying that something is monotone? Start with x less than y, then show that g of x is less than or equal to g of y. So we'll actually, in fact, we'll show that monotonically increasing. Uh, Monotonically increasing. So we want to show that g of x is less than or equal to g of y. Okay. So if we want to show that g of x is less than or equal to g of y, we want to consider this pa of x and pa of y. Is that clear? Pax, pay, because we want to talk about. So we want to show that we will show that gx is less than gy, right? But that is same as saying that what is how gx is defined? Huh? This pax is less than pay. Okay, capital Pax is less than Pa. So therefore it is all about partitions of a comma x and partition of a comma y, right? So you can start with let a, okay, which is equal to x naught, right? Or okay, less than x1 up to less than say xk, which is equal to x. Okay, a to x. This is a be a partition of the interval a comma x, of the interval a comma x. Is this clear? Hmm? So we have taken any general partition for a comma x. From this, can you give me a partition for a comma y? Because x is less than y, then this a, which is equal to x naught less than x1 xk, right? Then I will write
Yes, sir.
xk plus 1, which is equal to y, right? I will denote y as xk plus 1. So therefore this will become a partition of a comma y, is a partition of the interval a comma y. Is this clear? Any problem? This is a partition of a comma x and this is a partition of a comma y. Okay, then this implies this small pay regarding this one, small p, remember this is small p, that is summation, hmm, summation, what you will get, hmm? Tell me. For this partition, if you take this f, if you apply here, this is summation pay, which is f of hmm, xi minus f of xi minus 1. Of course, this is positive part of this, where I is equal to 1 to k plus 1, right? Because this is a partition from x naught to k plus 1. Is this clear? But this one I can write as summation I is equal to 1 to k, I will write. Then this is f of xi minus f of xi minus 1. And when I expand this k plus 1 term, what I will get? Here I will get as f of xk plus 1 minus f of xk, positive part. Is this clear? Are you following? Yes or no? Hmm?
Yes, sir.
Now, but what is this one? This is nothing but simply PAX, because at x is equal to
Yes,
k
sir.
up to here, this is a partition of this a comma x. Are you following? Plus this one, which is a greater than or equal to 0 term. Are you following? This xk plus 1 minus f of xk, positive part. We know that this value is greater than or equal to 0. This implies we got that this pay is greater than or equal to pax. Are you following? Yes or no? Hmm? Therefore,
Yes.
the capital Pay, which is supremum of all such things, is less than or equal to this Pay, and which is bigger than or equal to Pax. This is true for all partitions of the interval a comma x. Okay, so this implies Pay is greater than or equal to the small Pax for all partitions of a comma x, in particular by taking supremum of all these partitions a comma x, we get what we will get is that this Pay, capital Pay is greater than or equal to capital Pax. So remember this small p and capital P you should differentiate. Small p is for that particular partition, and capital P, whenever we are using capital letters, it is supremum among all such partitions. Yes or no? This implies we proved that this Pay, which is same as g of y, is greater than or equal to g of x. Right? So here you can use it equal also, no problem. So therefore we proved that G is, this implies G is monotonically increasing. Similarly, you can show that, similarly, this NA, whatever h of x we have defined, this is NA of x, right? So similarly, that also you can show that h is also, similarly, h of x is also monotone, right? Yes or no? Because what, even though you get here minus of that one, but that is also greater than or equal to 0. There is nothing different. So it is also monotonically increasing. Is that clear? Hmm? Any problem? Now we want to show that they are real valued. That means they take finite values whenever g of x is there. So for that, you can check that also. If you see, take this Pax, capital Pax, right? Which is positive part of that one, supremum. So it is greater than or equal to 0, right? This one is less than or equal to, we know it is less than or equal to Tax, and which is less than or equal to Tab. Now because our f is assumed to be bounded variation, so this value is finite. Okay, so this value is finite. This implies our Pa of x is nothing but g of x, which is also finite. So similarly, our h of x is also finite. Therefore, g and h are monotone real valued functions, right? Such that, what can you say about this g of x minus h of x, which is equal to Pax minus Nax. Now, by lemma, just now what we have proved here, if you see, Pab minus Nab is nothing but f of b minus f of a. So therefore, Pax minus Nax is f of x. Huh? Is that clear? So if you write this one,
Yes.
this is same as Pax minus Nax, which is equal to, hmm, what you will get? F of x, right? You see
Minus f of y.
f of x, we should get this is same as, hmm? So just this Pab minus Nab is nothing but f of x minus f of a, right? But we should get this is same as f of x minus f of a. That is, this one is just like b and this one, right? So this implies g of x minus h of x is this. So f of x is what? G of x minus h of x plus f of a. Is this clear? Huh? So you can rewrite this. This implies f of x is equal to, say I will write this as g of x minus h of x minus f of a. F of a is just one value, some scalar, fixed value, right? Now, if h is monotone, then h minus some scalar is also monotone. Are you following? This implies f is difference of two monotone functions. It is not exactly, our f is not exactly g minus h, but it is g minus h plus that f of e. That is the only thing. Is this clear? Yes or no? Hmm? So where our h is nothing but
Yes.
simply h of x minus f of e. That's all. Is that clear? Any problem? Hmm?
No, sir.
Now conversely, suppose assume that our f of x is equal to some g of x minus h of x, where where g and h are monotone. Monotone. Say they are increasing. The same thing is true even if they are decreasing also. Okay, say increasing. Then we want to show that f is of bounded variation, right? So if you want to calculate, take any partition and so on. You simply take any partition. They say just let this a, which is equal to x naught x1 up to xk, which is equal to b, be a partition of a comma b. Then what can you say about this value summation, because we want to find the t, capital T a comma b. For that we want to calculate summation mod f of xi minus f of xi minus 1. This value we want to calculate, which we denote as t, from I is equal to 1 to k, right? Can you tell me what is this value? This is nothing but summation I is equal to 1 to k, our f of xi, because our f of x is g of x minus h of x. So our f of xi is g of xi minus h of xi, right? Yes or no? Similarly, f of xi minus 1 is g of xi minus 1, okay, minus of h of xi, but minus of minus, what you will get is plus h of xi minus 1. Is that clear? This is same as summation I is equal to 1 to k. If we rewrite this, group them, you can write g of xi minus g of xi minus 1 plus uh, plus h of xi, uh, okay, you take out minus here, minus you take common, or plus, no problem, h of xi minus h of xi minus 1. Okay, now using triangle inequality, we know that this is less than or equal to, just like mod a minus b is less than or equal to mod a plus mod b. So this is summation I is equal to 1 to k mod g of xi minus g of xi minus 1, okay, plus summation I is equal to 1 to k mod h of xi minus h of xi minus 1. Okay, now because of the fact that this g and h are monotone, we already know that these values are greater than or equal to 0. So therefore this is simply I is equal to 1 to k g of xi minus g of xi minus 1, because those values are greater than or equal to 0, so absolute value won't be there. Similarly, plus I is equal to 1 to k h of xi minus h of xi minus 1. But now again, if you take expand the thing, only two terms will remain, that is namely g of xk minus g of x naught plus h of xk minus h of x naught, right? But xk is same as b, so what you have here is g of b minus g of a plus h of b minus h of a. Is this clear? Yes or no? So therefore, t, what we have proved is that is less than or equal to this particular value, namely g of b minus g of a plus h of b minus h of a, for every partition, for all partitions, right? For all partitions of this interval a comma b. So this implies if you take supremum of t is also less than or equal to this value, right? But we know the whatever right hand side we have, it is a finite value, right? That shows that this TAB is finite. So F is of bounded variation. Any problem? Huh? Is this is a very simple basic calculation. There is nothing to think so much. Huh? We simply take the value of f, which is g minus h. and find this value by putting wherever f is there g minus h and using the fact that they are increasing. Yes or no? Any problem? Huh? Have you understood the
No,
proof?
sir.
No, sir.
Have you understood the proof?
Yes, sir.
I
Yes,
see
sir.
only few people respond. Huh? You are the final loser. I am not going to say anything. If you have a difficulties, you please ask me. Huh? And if you are not, then you are the. So we'll just end with a simple one-line corollary that if f is of bounded variation, if f is of bounded variation, then f is differentiable almost everywhere. Then f is differentiable almost everywhere. Okay, I simply write a dot e. It is understood that it is almost everywhere. Can somebody give proof? It is very simple proof. Huh? It follows from previous result because f is of bounded variation. What you know? Huh?
If satisfied.
F can be written as g minus h, where g and h are monotone functions. Is this clear? Yes or no? Any problem?
Yes, sir.
So f is of bounded variation implies f can be written as g minus h for monotone functions g and h. This implies f dash, as we know that when we discussed about differentiation, we proved that g dash, if some function is a monotone function, then differentiation exists almost everywhere. That means it is differentiable almost everywhere, right? So as so we'll write as g and h are monotone. By known result, what we know is that g dash and h dash exists almost everywhere. Okay, this implies g dash minus h dash exists almost everywhere, right? But that is same as saying that f dash exists, right? Because f dash g dash minus h dash is nothing but f dash, right? Exists almost everywhere. Is this clear? So therefore f is differentiable almost everywhere whenever it is of bounded variation. Are you following? Yes or no? Hmm?
Sir.
Okay.
Yes,
Yes,
sir.
sir.
We'll stop here, and in next class we'll see some other properties. Okay, or some other concept. We'll stop now.